What in the world is an unparticle? I barely understood particle because under quantum mechanics, particle ain't a particle. Particle means a number followed by a unit, and they vibrate this number. They do all kinds of things. They say it's a field, vibration of a field. That's what a particle is. And field is a concept, bunch of numbers. So we never have anything solid to, put our munch to really chew on. And so, this is unbelievable. They invented new term, and this is a term you have to become familiarized with. That's what I'm going to be arguing today, and it's called unparticle. But let me show you something first. I can hear a brief introduction, and that is this is a article that came out there. It says it was reposted. It's an old article, but it was reposted. It says scientists find galaxy supercluster as massive as 26 quadrillion suns. And the question is this what science is about? Saying, hey, we found a lot of particles out there. We found a lot of stars. We found a lot of planets. We found a lot of galaxies. Is this what science is about? Talking about the many things that they see out there and just putting it on a little picture there or even a drawing and saying, hey, look at what we found. We found a lot of stars. And so what is this science? Just posting a picture of a bunch of stars? And this has a lot to do with the subject matter of today of the unparticle, okay? The unparticle. Let's start at the beginning, and the beginning is the Big Bang. Here's the Big Bang, okay? And they had this explosion, supposedly 14 billion or so billion years ago, okay? The famous Big Bang, okay? And that's how the universe started. Where did it start? Well, it was this singularity there. That first dot that you see there supposedly is a singularity. What is a singularity? Well, we have no idea because it's zero-dimensional, right? No volume. Therefore, no matter, no nothing in there. But suddenly this nothingness exploded. And that's the world we have today. And some people even challenge and say, well, it wasn't really an explosion. It wasn't an expansion. I have no idea how they visualize this because what they illustrate is just exactly that. An explosion, an expansion of something. It's like a hand grenade exploding. That's what you're staring at, okay? And so what does this turn into? Well, here you have it more or less, okay? Turns into that glass of wine or a glass of beer, right? That is sideways, okay? There it is. And so the explosion leads to this, and that was took 13.8 or 14 billion, rounding off, years ago. Okay, so that's what the explosion of the singularity leads to. Okay, and from that they come up and they tell you, okay, we can tell you what happened throughout this time, and here's like the history of the universe, of how different things were created along this this history, right? Some point you got the first particles and the nuclei, first light, stars, etc. So I guess there was no light when you had this explosion. Okay, that's interesting. That means you had just dark stuff being exploding from there, and it turned into light sometime later. And then you get the first stars, galaxies, and so on, right? And dark energy, which we're going to talk about today, is right there next to the last, just before today. So dark energy is really a new phenomenon, relatively, right? I mean, it happened relatively recently. Okay, so this is what the mathematical physicist or physics proposes. That's what a universe was all about. There was a moment of creation, no God involved. That's not what the religious folks say. They say, hey, you're missing God. God made the singularity, then everything took off. So what the religious folk have done is they've taken God and put it into the general relativity history of the universe and say God was first and then the singularity, and the other guy started at the singularity without God. That's the only difference. Otherwise, they both believe in creation. And the only thing you really have to ask to either group is, Don't tell me that God created it. Don't tell me that the singularity created itself or self-exploded or whatever. Tell me what the mechanism is, okay? Which is what good old Juanito Baez did not answer, right? He's saying that's not part of science and not part of physics. Yeah, what they want to do is a bunch of, they want to do a bunch of numbers, equations, and they want to get by with that. And no, physics is about the explanations, the mechanism, exactly what he's avoiding. Okay, so this is what we have here. We have this dark energy, okay, and it's pushing everything outwards. You can think of the black stuff there as the dark energy. We can't see it, that's why it's dark, and it's pushing all the visible stuff outwards, okay? And you get to this situation, okay, where you have, all the particles are going outwards, but then the question is, what is it, all this moving up against? Assuming, I put it as a circle because I'm assuming if it expanded from or exploded from ground zero, it's got to be circular or spherical, more or less, as it moves outwards. And the only question I've got is, what is it pushing up against? What is it, what's on the outside of this expanding bubble, right? Because, I think it's a valid question, because what you see, the dark stuff there inside the circle, is space that is populated or filled with dark energy. And so what's the black stuff on the outside if space is on the inside? And again, they say one of the answers you get is that it's an unscientific question. Okay, it's unscientific. Why? Because they say we have no way of testing the hypothesis. They put in words of that nature. And here, no testing is required. This is a conceptual issue, completely conceptual issue. You have to tell me what's on the outside if your theory is about to work. If you're going to say, hey, I've got a theory. What's your theory? My theory is that there was this explosion and all matter is expanding, all matter and space, right, is expanding and blowing up. Okay, what's on the outside of that bubble? It's a valid question. And they say it's invalid because they can't answer it. That's the issue. In fact, they can't even answer how the singularity, what's outside the singularity, especially if the singularity is zero-dimensional and no volume, no shape, no size, no radius, no diameter, no nothing, no matter. So, yeah, I don't know if you can put anything outside of what is already nothing. What are you going to put? Nothing outside of nothing? So this is where we're at. That's the state of the art in physics. Okay, so this is what they're saying. They're saying that dark energy fills the space all around galaxy, meaning around every star and every every planet or asteroid or whatever. And this is a problem because either you put it on the outside, like they do with dark matter, and if you put it on the inside, we have a problem because then we should be blowing up, and dark matter should be pulling it inwards. And they always put the dark matter on the outside, on the periphery of a galaxy. And as far as dark energy, no one has specified that where it's at. They like to look at the big picture and say, look, dark energy pushes all these galaxies apart, but they don't tell you whether dark energy is between the Earth and the Moon, at this level. Is it between you and me? Do we have dark energy pushing us apart because it's blowing up, it's expanding, right? It's pushing everything apart. Are we getting separated because dark energy is between us too? And so these are valid questions, and they never deal with those questions. They want to do math. That's all they want to do, equations. And they're looking for ghosts and spirits somewhere out there that are pushing the galaxies apart. Okay, and so here you see it. Again, this is the balloon analogy. And what's the problem with this? The problem is that it's going to push, see those curlicues there? Well, those are light. That's light. And so they're saying as the universe expands, as space expands, as dark energy compels everything to expand, the wavelengths become longer and longer and longer. That's the argument. Okay? And so this is kind of strange because, that would mean that I guess light would have a different speed. And they say no, and this is important for the argument of the unparticle, because it's a scalar thing. You can make it bigger, nothing changes. The speed remains the same. Okay? And so this is interesting because they're saying, hey, you know, even if the universe expands and it stretches the wavelength of light, we wouldn't notice. We would measure the same speed because, you know, the fact that it becomes bigger just makes everything become bigger. I guess you're getting bigger as well. I mean, I don't know if you're bloating up like a toad, like a smoking toad. So, you know, keep those issues in mind, okay? Okay, here we have dark matter and dark energy, okay? We have the percentages. Dark energy, they say, is, they claim, maybe it's 73% of what's out there. Dark matter is maybe 23%. And the luminous stuff, the stuff we can really see, is only 0.4%. Okay, so we have a lot of matter there that we cannot see, which they haven't identified really. They have dark matter, they have dark energy, and some people turn this around and say, hey, you know, this is really a measure of how much we really know about the universe. And yeah, I would say that's really the case for mathematical physics. I think that what they know is really 0.4%. That's all they really know. And all the other stuff they don't know anything about. And so they're inventing all these terms, okay, dark energy, dark matter, and whatever, what have you, because they have no way of explaining. You know, they don't have the why. They have no mechanisms for how this universe works. So they have to put in these terms. They say, oh, it's dark energy. Well, what is dark energy? Well, we don't know. We're looking for it. Okay, so it's a measure of their ignorance. That's all it is. And so there was an article, and that's what got me into the subject matter today. There was an article recently published, and this is what they propose. They propose the unparticle. They say it's not dark energy, it's the unparticle. Okay, so what the hell is the unparticle? So we have unparticle physics is a speculative theory that conjectures a form of matter that cannot be explained in terms of particles using the standard model of particle physics, because its components are scale invariant. Okay, scale invariant, what the hell is that? So let's look at that real quickly. Okay, here it is. Scale invariant means the following. It says, is a feature of objects or laws that do not change if scales of length, energy, and other variables are multiplied by a common factor, and thus represent a universality. The technical term for this transformation is dilatation or dilation, either one. Okay, so that's what they're talking about. They're saying something that doesn't change in scales. And that's more or less what I said earlier about light being stretched. You know, you wouldn't notice because everything remains the same regardless of how big you make it. Okay, so that's more or less what scale invariance means. And that's like, this continues. I think this is out of the Wikipedia. All particles exist in states that may be characterized by a certain energy, momentum, and mass. Okay? In most of the standard model of particle physics, particles of the same type cannot exist in another state with all these properties scaled up or down by a common factor. Electrons, for example, always have the same mass regardless of their energy or momentum. But this is not always the case. Massless particles, such as photons, can exist where their properties scaled equally. Okay, so you can make a massless particle bigger, no problem, because it's got no mass, so don't worry about mass. But this immunity to scaling is called scale invariance. The idea of unparticles come from conjecturing that there may be stuff that does not necessarily have zero mass, but is still scale invariant, with the same physics regardless of a change of length or equivalently energy. This stuff is unlike particles and described as unparticle. The unparticle stuff is equivalent to particles with continuous spectrum of mass. So this whole thing was invented by a fellow to explain particles that have some amount of mass. You know, they're exactly or more or less like photons. Remember, the photon is allegedly massless. It's when it's standing still. It's got no mass, they say. It only has mass or energy or whatever they fill it with when it moves. And here we have something that when it's standing still, it still has a tiny little bit of mass, but it doesn't interact well with things, with matter, with the stuff that does exist. And that's how they get around it. They say, hey, we haven't detected it because it interacts very weakly with matter. So they have all these things like neutrinos, they all interact weakly with matter, meaning that they invented a term that they needed in their equation, but they can't find it. And they say, we can't find it because it interacts weakly with matter, because either it has very little mass or it's scale invariant or who knows what. They have some excuse for why they can't detect it. And so they try to detect these particles through experiments, right? And they say that particle is there because we need it in the equation. But let's find out how we can detect it now. And yeah, they're talking about ghosts and goblins and who knows what. And the most famous one of those, are the virtual particles. They look more or less like this. They pop in and out of the vacuum. Okay, and so they say these particles form part of the vacuum. In other words, they are really part of this dark energy, right? Virtual particles, they all mean the same thing, really. These are ad hoc things that they put in there because they want to be able to make the equations come out right. And they say, well, something happened here that we weren't able to see. There was a difference in the measurement, and so what do we put in there? Well, let's put a spirit in there, and that spirit's called dark energy or virtual particles or unparticles or whatever they have out there. Okay, and so yeah, so the issue is that they're putting all these new words, and then dark energy being replaced now by the unparticle. Okay, and that's what the unparticle looks like. If a particle looks like something that has shape, the unparticle, I guess, looks completely dark, nothingness. Particles that don't have shape, maybe they have a little bit of mass because they're scalar invariant. Who knows what? They invent all this nonsense because they need to plug holes in their theories. It's all ad hoc. None of it has any reality whatsoever. And that's why people have lost interest in so-called physics, what the mathematical physicists call physics. Because it's just boring. They just invent new terms and then they say they proved it. And here you have another fellow who proposes something else other than unparticles, and he's got another explanation for dark energy. And he says the following. He says the universe is twice as old as anyone thought. Okay, and he goes in there and says the universe might be almost twice as old as we believed, being 26.7 billion years instead of, I guess, the 13.8 or whatever, 14.8, right? And he wrote this some time ago, so it was 13.7 at the time. He raised that to 14.8 or 13.8, I guess. It says the new theory suggests that the universe might also be made completely of different material from what scientists previously believed. And what is this guy proposing? He says, rather than requiring mysterious unseen dark matter to make up everything, it's actually to do with forces of nature decreasing over time and light losing energy. Okay, and this is what he's proposing. He's saying that in standard cosmology, the accelerated expansion of the universe is said to be caused by dark energy, but is in fact due to what? The weakening forces of nature as it expands, not due to dark energy. Okay, so we have some people who propose that, I guess, energy gets tired, as it expands. So it's not that there's dark energy there, but there's some kind of matter that weakens as it expands. The other guys propose unparticles, say it's not dark energy, which has a specific definition for mathematical physicists, than what these other mathematical physicists are proposing. And so they say, look, the unparticles, they can solve our problem. We don't have to do all that dark energy stuff. It's just the unparticle, which has a little bit of mass, and they play around with the numbers and try to show that it's dark. It's the unparticle that really replaces dark energy as the fuel that expands, that pushes outwards all the galaxies and all that stuff they're measuring out there. What's the issue? The issue is that all these people write a paper and they claim at the end of it saying that, you know, someday, maybe 10 years down the road, when we have more technology, more proof, more tests, more experiments, someone will corroborate what we just said 10 years earlier. And so they all get a Nobel. You know, the guy says, hey, I was the first one to propose the unparticle. And he says, someone will prove it in the future. So the guy in the future has nothing to do at his desk. He says, oh, what do I do? How do I get a Nobel? How do I get my paper published? So he publishes a nonsense poppycock paper on unparticles or tired energy or whatever. And that he proves mathematically that is the case. And he proved what the guy did 10 years earlier, and they both get a Nobel. The guy who came up with it first and the guy who proved it. And so they both share in the Nobel Prize. And that's how this whole thing works. You know, the black holes were proven like that. One guy proposed it sometime in the past. Then a few of the mathematical physicists ran with it. And at some point they proved it. They said, we saw it, we photographed it, and now we corroborated it. And then the guy who came up with it, you know, he gets a Nobel if he's still alive, and the other guy who proved it for sure gets a Nobel. And that's the way it works. But their names get, you know, put in lights, and that's what's important. Okay, so here's the space-time field. That's what this dark energy is all about. The so-called unparticles. How do these particles come into existence? And this is how they visualize them, more or less like the ether is. In fact, no different whatsoever. So space-time or general relativity is an ether theory. There's no difference between ether and what's you know, the general relativity proposes. And here it is. Here you have your space-time. This is two-dimensional. You could say 3D vision, 3D vision superimposed on a 2D platform or whatever you want to say there. And that's your space-time. That's the starting point. Suddenly we're going to put a particle in there because what you're staring at is a field, what they call a field. And what is a field? Well, it's a bunch of those lines. And what are those lines? Is that a canvas? Is that a trampoline? Is that a fishnet? No, what you're staring at is what we covered last week, and that is number lines. Okay, they're not even dimensions or coordinates or vectors. They are number lines. What you're staring at is each one of those lines is direction and magnitude. And what they're doing with that is they're shaping the number line itself. Okay, and so this is the aggregate of all those gives you this space-time thingy. Okay, that's what they're going to use as a platform to explain gravity, or in this case, the dark energy that is pushing the universe apart. Okay, and here you see how the particle comes into existence. It's just a localized special vibration of the field. That whole thing is the field, right? And they're going to have this particle pop in there from the vibration of the field, local vibration of the field. That's how they visualize these particles. You know, what is a particle? It's a vibration of the field. That's what they're saying, localized vibration of a field. And but then they have to do something with it. They can't just leave it with the field. And so what do? Well, they have to show that this thing somehow interacts with one particle interacts with another. How do they do it? Because if they're separated, if they're isolated, how does one particle, interface or interact, with another? That's it. When they're far apart, they're isolated. Turns out that the way they visualize it, it's not isolated completely. And so here we see how an exchange of energy occurs according to general relativity. Here it goes. You can see the particle there, right? And now you have this field, another particle. You have all these quantum fields there, right? And then they have this exchange of energy. And they exchange energy, simply by the way it is, okay? And so this is the problem with all these people. Let me show you that again. Here it is. You can see the particle, and then you have all these fields. They intervene. And what it is, a bunch of fields, which is this space-time, this dark energy or unparticle, whatever you want to call it, and then it turns into these particles, simply a local vibration. Then you have the particle, and then you have the exchange of energy through the field, through the space-time. Okay, that's how they do it. So they have this nonsense in their head because they're talking about number lines, which they're shaking, and they're saying it's through the number line that they're that particles are communicating with each other. Okay, and so that's the state of science. Okay, or you can call it science. Okay, what do we say? Well, you need to identify the objects. You need to identify the objects. So you don't know, you can't see it or you can't touch it. There's something there. They call it a field, they call it energy, whatever they call it. You know, time, doesn't matter, force. Okay, so you have something in there that you don't understand because you haven't seen it, you haven't touched it. And you cannot run an experiment on that which is invisible and intangible. And so this is what these people think they're looking at. They're looking at discrete particle and they say, oh, these are discrete rabbits. They're jumping around from one place to another. And you say, okay, how do you know they're rabbits? Well, what else can it be? You know, that's more or less the answer you get. And it turns out that, yeah, there are different ideas out there, and here's one, okay? It could be a snake, maybe that's, or a worm that's twirling in place, okay? Maybe nothing is moving from A to B. So what they think are jumping rabbits is maybe a worm that is twirling in place. And so they haven't considered that ever, you know, especially for the force of pull. And then the other issue is, you know, they have these, so you do need to identify the object in order to be able to do your math. Because if you're doing math on rabbits and it turns out what you're really staring at without knowing, you know, that invisible, intangible thing that you're looking at or thinking about is really a worm, a torquing worm, then your math is all screwed up. You're doing math on stuff that is not out there, okay? But then you have the issue of field. You know, they have this field, you know, and then a localized vibration of the field becomes a particle. But you got to tell me what the field is. Don't tell me that a particle is the vibration of a field. Okay, then we got to forget about the word particle and let's look at the field. What is a field? And a field is a bunch of numbers. That's all it is. And then you have, you know, like between two magnets, right? There's some object or some thingy that we can't see or touch. And they call it a field. They say it's a magnetic field that's in there. Okay, no problem. Call it a field. I don't care. Show me the field. What does it look like? And they say, well, we can't because it's infinite. It extends to the edge of space-time, and space-time is pushing up against nothingness. Includes space in there, but they're pushing against space, I guess, on the outside. I don't know. They have to tell me. But they never identify the things, the objects. And that's why Mr. Bias cannot tell you, you know, he can't give you explanations. And he says he can answer the why questions. Of course not, because he's not doing physics, he's doing mathematics. That's why he can't. And so he thinks that equations are physics. And so here, I showed this the other day, but let's show it one more time. Okay, and here it goes. You have this fellow jumping with a rope, and the object is the rope. The region we're scanning is known as a field. And so we cannot confuse the rope with a field. Okay? The object is a rope. Okay? And the region is known as a field. And so they can't say a field does this or that a particle is the vibration of a field. That's irrational language because field is a concept, some mathematical concept. And you cannot say that, oh, it's because the field is vibrating that creates a particle and I'm going to use the particle now. Now, you can't use the particle because you still haven't identified what a field is, and a field is not a thing. Field is a region of values. That's all it is. And so you have to identify the thing that is creating that region, the thing that's moving in that region. And that's what they've never done, okay? And so, you know, so again, when they talk about dark energy or unparticles or any of those terms that they invented and they introduced in their dissertation, they're not giving you any explanation of anything. They're trying to give you an explanation, but they don't have an explanation because they're really talking math. When you put them against the wall, they'll give you an answer like Bass did, and he says, well, you're asking a why question. You're asking a mechanism question, you know, and you came to the wrong place. We here at Cambridge, we here at Harvard, we don't do those things. We do just math. And so you have to wonder whether the unparticle that they're talking about, is that a math? Because they're talking about slight mass and they're talking about the fact that it's scalar, invariant. And does that belong in physics? Or are we just talking math? And that's more or less the state of the art of physics, mathematical physics.